Okay, so maybe it's time to start again with the last talk of today. Our speaker now is Masanori Hanada from University of Surrey, and he's going to talk about black hole from matrices. So please, Masanori, you can start.
Okay, thank you very much. Actually, I wanted to be in APCTP physically, but I didn't have enough time to get a visa to go there. So I hope soon everything go back to normal and I can visit physically APCTP next time. Okay, so today I want to explain how black hole can be described by using matrix model and how numerical method can be used to see that. And we will do it by using holography. Via holographic principle, black hole or more generic quantum gravitational system can be related to non-gravitational systems. They are secretly equivalent. And this side, non-gravitational system, can be matrix model or super YAML theory or SYK model, all kinds of non-gravitational system. And so in this famous picture of a hologram, this is a black hole, and this is a matrix model or super YAML's SYK model. And we cannot really touch this black hole directly, but by touching this side, we can actually touch it. And if he doesn't fight back, we can break him and see inside. And we can learn how black hole is described. This is the idea. So we want to study this side. And so this is first papers which suggested this kind of idea by Tofu and Sasuke. They claim that our world with gravity is secretly non-gravitational via hologram. And we want to study this side. Okay, and then by studying this side, through the equivalence, we can learn about quantum gravity. This is the basic idea. And I want to explain that the lattice simulation, a Monte Carlo simulation using basically the same as lattice gauge theory has been very successful, and we can learn many things. And I will spend most of the time to this part. But there are several fascinating problems, very interesting problems, which is very difficult, and we cannot use Monte Carlo simulation to study such a problem. And for such problems, quantum simulation and machine learning can be useful. And I want to give some short list of interesting problems to which new methods can be useful. The concrete model we study today is a so-called DO-brane matrix model, this is often called the BFSS matrix model. Many of you in the audience are probably not string theory from string theory community. Then you don't really have to worry about the detail. So basically, this is a quantum mechanical system, not QFT. So we don't have continuous spatial directions. We just have a time direction. And the variables are n by n matrices. So this X is a bosonic matrix, bosonic n by n Hermitian matrix. And this is psi is a fermionic n by n matrices. And this D is covariant derivative. So gauge field along temporal direction is secretly hidden. Or in Hamiltonian formulation, we impose a gauge singlet constraint. And they have certain complicated interaction. If you know Miller theory, this is just a dimension reduction of the 4-dimensional maximally supersymmetric YAMLs to 0 + 1 dimension. And for example, this commutator square comes from field strength square, if you know that. Historically, in 1998, DeWitt, Hoppe, and Nicolai proposed this model in the context of supermembrane. So it was known that string is 0, particle is a point-like object, string is a 1-dimensional object, and the membrane is a 2-dimensional object. And it was known that supermembrane can be consistently, supersymmetric version of a membrane can be consistently defined in 11 dimension. And this matrix model is somehow related to supermembrane. And we can use matrix degrees of freedom to regularize continuous degrees of freedom on membrane, and they could get to this model. And in 1996, Banks, Fisher, Schenker, Susskind, whose name is in this BFSS, they proposed, gave a new interpretation to this model, and they claim that this model can be described M theory in certain situation. And then in 1998, Itsaki, Maldacena, Zonesha, and Yankirovich suggested that in a somewhat different parameter region, this model can also describe type 2A black zero brane. And black zero brane is if you don't know it, you can just think it's black hole. Yes, some sort of black hole. And I want to study this model. And first, we study parameter region which corresponds to type 2 superstring theory, as proposed by Itsaki, Maldacena, Zonesha, and Yankirovich. And here we want to show that the numerical simulation is useful to do very precise test of duality. And I also want to show more recent result, which suggests that M theory can actually be described by this model, as suggested by Banks, Fisher, Schenker, and Susskind about 25 years ago. And the second part is somewhat speculative. According to the proposal by Itsaki, Maldacena, Zonesha, and Yankirovich, so not just this model, but more generically, Yang-Mills theory, super Yang-Mills theory with the UN gauge group. Oh, I said just matrix, but it's N is used to denote the size of matrix. Okay, and so model of matrix super Yang-Mills theory with the UN gauge symmetry, whose degrees of freedom are matrix valued field, and each matrix is N by M. And we can define it in P spatial plus 1 time dimension. And this is, if you know string theory, this is a system of so-called DP-brane and the strings connecting them. And this P can be 0 or 1 or 2 or 3. And P equals to 0 is a black hole, correspond to matrix model. And such system is a dual or equivalent to so-called black P-brane in type 2A or 2B string theory. And black zero brane is a, so this P means a spatial dimension. And if you have a black hole, if you see black hole from far away, it looks like a point. So it's a zero brane. And you can imagine that something like an area of a black hole, which is forming a string-like shape. Then see from far away, it looks one-dimensional object. Then it's called the black one brane. And you can also imagine black two brane or three brane. Okay, so such black hole-like object in string theory corresponds to super Yang-Mills theory. And if you take a P equals to 3 case, this is a famous ADS CFT correspondence. ADS CFT correspondence, but it can be more general. That's what these people claim. And we are focusing on P equals to 0 case. So what we are talking about today is a special version of much bigger duality, including ADS CFT duality. And in this paper, so they gave analysis for various supersymmetric theories with different dimension. And in the case of P equals to 0, this is coupling constant of the theory. And we, not just Yang-Mills coupling, we multiply N to take so-called two-fifth limit, two-fifth coupling, and we fix this and take large N limit. So there are many degrees of freedom. And if we fix a coupling, then because there are many fields, interaction becomes too strong. But interaction between each degrees of freedom becomes smaller. And at the same time, number of degrees of freedom goes up. Then as a whole, finite amount of interaction can survive. So two-fifth limit is such limit. Okay, so this is fixed and then it's set to infinity. And then this two-fifth coupling is dimensionful when P is 0. That means we can use this coupling to as a convenient unit to measure any dimension of full quantity. So for example, if energy is high or low, can be measured by using this unit. So this Tofut coupling times energy to the -3, because energy has dimension of the mass, this is dimensionless. Okay, so if this combination is small, that would mean it is high energy. If this combination is large, this would mean low energy. At the same time, this combination plays a role of shortless coupling constant, because this is coupling. So low energy and the strong coupling are essentially the same thing in this theory. Okay, and duality between gravity and non-gravitational theory is good at the strong coupling at large N. So in this theory, if we go to very low energy, this side just becomes pure, like something like Einstein gravity, quantum collection drops. And in this limit, so large N and the strong coupling, they estimated the energy of the black hole by using Einstein gravity. At the same time, that should be interpreted as energy in a quantum non-gravitational system. Okay, so energy, black hole mass is energy, and that should be identified with the energy of the corresponding non-gravitational system. And the temperature, Hawking temperature is a temperature of black hole, and that should be identified with the temperature of the non-gravitational system. And once a temperature is fixed, energy is also fixed. Okay, and they used a standard formula called Becker-Stein-Hawking, and obtained that this energy is some calculable number, which turns out to be 7.4 times n squared. This n was a metric size, times this specific power of coupling constant times this specific power of temperature. And this may look very strange power, but power counting doesn't really matter in this case because lambda has dimension. So this combination has precisely the energy, a unit of dimension of mass. And because this lambda is just gives a unit to measure the dimension of quantity, we set this lambda to be 1 from now on. Okay, whenever you want to recover lambda, you just insert appropriate power of lambda so that the dimension matches. And but checking this is very standard thermodynamic simulation to which Monte Carlo approach can work. Okay, so that's how very standard lattice gauge theory type calculation can play a role in string theory. So we can use a Monte Carlo simulation. We can do Monte Carlo simulation by using technique from lattice gauge theory. Like this is a very standard technique used in lattice QCD community, and we can just learn from them and apply. And there are some differences, but we can, depending on the detail of the theory, but we can work it out. And so some small changes needed, but basically we can use many techniques, which are already prepared by lattice gauge theory people. And now this statement itself is true, not just p equals to 0. Positive p is also fine. But if you imagine regularizing the space-time by using lattice, okay, so here we want to do thermodynamics. So we Wick rotate Minkowski theory to Minkowski signature to Euclidean signature, and we introduce a space-time lattice. Okay, so if we have a p plus 1 dimension, p space plus 1 time direction, then we need a p plus 1 dimensional lattice. And imagine that we have L0 lattice point along time direction. And if we want to do thermodynamics, we want to take the size of the imaginary circle to inverse temperature beta. And we want to take a number of lattice point to be of order of beta. Okay, so at low temperature, we need more lattice point. But if we have a more non-zero spatial dimension, we have to introduce lattice to that direction as well. And imagine that to first, second, and p direction, we have L1, L2, and LP lattice point. The number of lattice sites needed is a product, of course. And then, of course, if we have a lot more lattice points, then simulation becomes harder. because we have to put the field at each lattice or link, lattice side or link. Then, of course, p equals to 0 is the easiest because lattice becomes smallest. And if p is 0, we don't have this part. So instead, we can go to larger L0, which would correspond to stronger coupling, or larger value of N. But if we go to non-zero spatial dimension, then we have this part. So we have to sacrifice computational resource for this part. So maybe we cannot go to larger N, or maybe we cannot go to lower temperature. Okay, so anyways, so p equals to 0 is easier. So we want to focus on this set. And from a quantum gravity point of view, whether we study p equals to 0 or non-zero field, there's no difference. P equals to 0 is already sufficiently interesting, or arguably more interesting than non-zero p. And there's a so-called sign problem, which would mean weight, path integral weight is not necessarily real and positive. And in many cases, we can check that just dropping the sign of the weight, we can get the right answer. But it's not established completely. There is no theoretical justification, but phenomenologically, we can show that we can drop sign. So we will take this approach. And we are doing this for more than 10 years by now. Okay.
So previous slide is the Kenshi, phase Kenshi is just dropping the phase.
Yes. Yes. So we have a action, Euclidean action S, and the path integral weight is exponential minus S. But S has a real part and imaginary part, and we drop imaginary part of S.
So each step.
No. Sorry. That's not. Yes. Imaginary part of S is dropped.
So each step you just drop, just neglect this phase and calculating. Is that?
Yes, that's what we do. So the theory we study is that lattice action is not exactly the same as original theory. Imaginary part is dropped. But yes, that's what we do.
So how do people recognize whether there is a problem or not? Like if there is sign problem?
So for example, there are in many cases, it's known that by dropping sign, we get the wrong result. We can give such examples. For example, finite baryon density QCD is such example. With and without phase, we get completely different result. And what we have done so far is that when a system size is small, say when n is not too big, we can estimate the effect of sign numerically. Okay, there is a way to do that. Very expensive, but we can do if metric size is not too big. And then we can show that the result doesn't change with any error. And numerically, we can explain how that is happening. But we don't have a precise understanding of the physical reason why that is happening. So that's the reason I said it's phenomenologically okay. And also, if we talk about this duality, it may be a bit of cheating, but we have gravity calculation on this side. And then we can see if phase quench simulation on this side precisely agree with the dual gravity calculation. And somehow it also works, even when we cannot really numerically justify the phase quench. So there must be a reason that phase quench, is fine, but we don't know the precise mechanism for that. So if anybody can find the explanation, that's great. And that's partly the reason why I want to suggest that other technologies can be used. Because if we use other approaches which does not suffer from the same problem, then we can make the result much more convincing. The same problem is a technical problem associated with the Monte Carlo approach. If we take other approaches, it may not be a problem.
Thank you.
Thank you. Okay, so anyways, so we went to very big lattice size and also very fine lattice. And then back in 2016, these two people, Enrico Rinaldi and Evan Barkovits, who were in the Livermore lab at that time, did really great job, and we had a very fruitful collaboration. And we used a K-supercomputer in Japan and the Vulcan in the USA to, oh, by the way, very sadly, they are not available. At that time, they are really good computer, but after 3 years, it was not really good anymore, and they retired already. They don't exist anymore. Anyway, but they were a really good fast computer at the time. And in collaboration with these people, we did the simulation for many parameters. So many different values of matrix size, different values of temperature. And for each of them, we studied the multiple lattice sizes. Okay, and we got this plot. So this is energy divided by L square. And this direction is temperature. And the low temperature is a strong coupling. High temperature is weak coupling. And we estimated the infinite n. We had a few different values of n. So typically like 16, 24, 32, and we extrapolated to infinite n. And we had different lattice sizes like 16, 24, 32, 48. And then we extrapolated to continuum limit. And we showed only continuum value of the matrix model. And this line is a supergravity result. So 7.4 times t to the 14/5.
Sorry, we have a question.
Yeah, I have some questions. The first question is that what is your lattice Fermion model? Yeah.
I mean, you're asking about the detail of the lattice regularization.
No, I just say is you use the Wilson Fermion? Well, or not?
That's not slightly different from Wilson. So it's not Wilson Fermion, and also it's 0+1 dimension. So actually, the detail of the regulation doesn't really matter, and it's almost like naive Fermion. And but I added some 3-level improvement factor. So I can show, I didn't prepare the slide, but after the talk, if you're interested, I can show you the explicit lattice regularization.
The second question is
it's different from Wilson or you would imagine from QCD, but it's very similar.
Okay, let me ask a second question. So I think because you use quantum mechanics model or matrix model, so you do not need to do the enumeration to extract the physical parameter from the Bayer parameter. So if I want to study the one-over correlation, I think that I should get some enumeration effect. Is it correct?
So say it again, say it again.
I say, because now you just consider 3 level, one leading order. So you do not need to consider the enumeration effect to extract the physical parameter from the Bayer parameter.
So 3-level is gravity sense, you mean?
Yeah, 3-level, yeah. So in this sense, you do not need to do the enumeration. I mean that usually in the lattice QCD, we need to define the physical parameter from the Bayer parameter for study of the RG. But now you only consider 3 levels, so you do not need to do that. I think it's fun.
I mean, renormalization in the matrix model side.
Yes,
that's a good point. And so there's a difference in 0+1 dimensional theory and the QFT. And so for example, it's 0+1 dimensional theory. Okay. So what the kind of renormalization you're talking about is renormalization of Bayer coupling, I think. Bayer coupling defined at the regular cutoff level.
But I think that the matrix model is just a low energy effective theory because you do the dimension reduction from the UV complete theory equals 1.
Yeah, but let me explain. Give you a precise explanation. And like people like Arnold Joseph, David Shake, or Raga Hofscher, who are participant of this workshop, they study supersymmetric chemicals, 3+1 dimensional version of this, or 2+1 dimensional version of this. Okay, and in a higher dimension, there are UV divergence. Okay, but in 0+1 dimension, unless you do take very stupid regularization, we don't really have UV divergence. And in that case, actually, renormalization associated with UV behavior is not really needed. But for example, if you want to do 3+1 dimensional version of this duality, you have to maybe you have to renormalize the coupling precisely, or you have to at least you have to worry more about that.
Yeah, but
it also depends on lattice action.
Yeah, but if we want to see the dual of string theory, I think in precise we should do a 3+1. Is it correct?
Say it again, in the dual side.
If you want to see the dual of string theory,
yes.
Then we should do the dual. We should study the 3+1 dimension boundary theory. Matrix model should not be enough. Yeah.
No. This 0+1 has a precise gravity dual.
You
so
say,
that's a very important point to say. ADS safety is just a very specific example of gauge gravity duality.
Would you say the dual for large N or the 1/n correlation to all orders?
So that's something we motivation of this study. Okay, so more precisely, proposal by these people. Okay, so at large N and strong coupling, supergravity is a precise description. And around there, large but finite N and strong but finite coupling, you can have a perturbative expansion of 1 with respect to 1/n or 1 coupling.
Yes.
And the strongest version they suggested is that expansion also agree, and including non-perturbative effect, even including non-perturbative effect, matrix model and type 2S superstring has to be equivalent. But that's something we have to check, right? And then actually, that's a very good point. And here I show the large N result, but we still keep coupling to be fine, right? Then we can see if stringy alpha prime collection matches with a finite coupling collection in matrix model side. Or when we take a large N extrapolation, okay, so they, as a byproduct, we can get the coefficient for 1/n expansion. And then we can check if that agree with the gravity or not. And what I can tell you is it seems to be perfectly the same. So those 1/n correction or 1/coupling correction appears to be precisely the same as J string correction or alpha prime correction in gravity side. So I believe this duality is beyond the supergravity.
Okay.
But such correction is extremely hard analytically on non-gravitational theory side. So that's the reason numerical simulation is really important.
Okay.
Like here, this reading part. So this and this A0 equals 7.4. This is supergravity, but alpha prime correction can be estimated in the string theory side to some extent, and that gives this specific power, so higher power of temperature, and this is a reading correction in terms of alpha prime, and this is a next reading, and so on. So we tried such others as well. And what we can say is, so this is reading this is supergravity, and these two. So these power can be determined from string theory, but this order 1 constant B and C, we cannot analytically determine from string theory. In principle, we can, but we haven't been able to. But this kind of expansion is predicted from string theory if duality is correct, including stringy correction. And then we compare we could see that this value obtained from matrix model, we left A and B and C as a free parameter for the fit. Okay, and we introduced 3 parameter and not 4 parameter because if we have too many parameters, we can fit anything. But then, for example, we could get this A to be very close to 7.4. So this is a good indication that at least supergravity is realized. And for example, we want to test if this specific power is reproduced from a matrix model. And of course, we cannot introduce too many parameters. So we took this part and this specific power to be a free parameter. And we have to assume that the difference between these two terms, this one, we have to keep it fixed because we didn't have too many data points. But then with this fitting ansatz, we could get P equals to 4.6 plus minus 0.3, which is perfect agreement with this. And if we take different power or different kind of correction, we cannot really fit the data. So it seems that including a stringy correction, this duality is working. And to do more precise test, now we have more people in the collaboration. And Stratos Paterodis is a student in Regensburg, and now he's writing a PhD thesis. And in his PhD thesis, probably we can show a few more points here. So please stay tuned, and we can show the result very soon. But it seems that the duality is perfectly working. And that was about type 2A string theory. And we also want to know if M theory can be described in this theory. So basically, we took two-fifth limit, which is so energy times log n is fixed, and that's not too small. And this is a picture taken from these people's paper. And if we fix n and go to much lower energy, then M theory should appear, and that might be related to BFSS proposal, according to Itsuaki, Maldacena, Zonesha, and Yankinovich. And in their argument, the way they argue that is that if a black hole becomes small, size of the black hole becomes smaller, a stringy correction at the horizon scale becomes much larger. They could argue that because they had a gravity estimate on that quantity. And then what they suggested was that if we fix n and go to very low energy, then string coupling at the horizon scale becomes large. But according to Witten's famous argument relating type 2A string theory and M theory, large string coupling would mean string coupling is somehow related to size of 11th dimension of M theory. And if string coupling is not too big, then 11th dimension is compact fine, and it looks very small. And then it looks like 10-dimensional space. But if a string coupling becomes very large, then 11th dimension should open up. And seen from the black hole, if a string coupling at the horizon scale is not big, that would mean that the horizon scale of the black hole, horizon of the black hole 11th dimension is not too big. Then if Schwarzschild radius is bigger than that 11th dimension, then so this direction is 11th dimension. But if Schwarzschild radius is bigger than that, then black hole completely fills that small 11th dimension. And it looks like it's completely filling 11th dimension, and it looks like a uniform string. Then 11th dimension doesn't really matter, and the 10-dimensional gravity solution is fine. But if 11th dimension becomes larger and larger, at some point, 11th dimension is much larger than Schwarzschild radius, then black hole cannot fit in this 11th dimension anymore. Then see from black hole suddenly realize that he was actually living in 11th dimension. And that happens at low energy. So as the energy becomes smaller, Schwarzschild radius becomes smaller. At the same time, string coupling becomes larger. So 11th dimension opens up. And at some point, black hole suddenly realize that, wow, I was living in 11th dimension rather than 10th dimension. And according to these people, such phase transition should be captured in this matrix model. And I want to check it. And so what would happen? How such physics should be described in this matrix model? And in a lattice approach, we do Euclidean path integral So we fix temperature and perform a Euclidean path integral, okay? And so it's canonical ensemble. And we take large end limit. And according to Itzhaki and the collaborators, in this limit, we have a good type 2A description. T fix would mean E, energy fix. And the finite temperature would mean finite energy. And so we have energy goes up, starting with 0, it goes up, and proportional to n squared. And the Polakoff loop is a trace of Wilson loop winding wrapped on the temporal direction, and which is a good order parameter of so-called deconfinement. So if Polakoff loop is non-zero, this is the confined phase, and it can increase all the way up to 1. And in confined phase, energy has to be 0. But if P is non-zero and the system is in the confined sector, the confined phase, the energy has to be order 1 quantity times n squared. So energy divided by n squared should start from 0, but it goes up. It's everywhere non-zero at except for exact 0 temperature. And that phase corresponds to type 2A supergravity. And that was believed in past 20 years or so. And this has been confirmed very precisely. I showed a very precise numerical result. But we want to claim that actually at any temperature, there is one more phase, which is also free energy minimum, but it's a local minimum. And if we free energy is larger than the confined phase, so in that sense, it's not dominant in path integral. But there must be a confined phase where energy is 0 up to 1 by the correction, and the Polakoff loop is 0. And more precisely, at the finite n, we suggest this picture. So this is the confined phase. And in infinite n, this deconfined phase continues all the way to 0 temperature. But at finite n, it has to disappear. And at this point, approaches to 0 as n becomes large. That's already suggested by Itzhaki and collaborators. And then after this point, what happens is we have a black string or localized black hole phase. And that is actually this dotted orange line. So this phase, this phase and this phase corresponds to this. And then at some point, black hole completely evaporates. That is this confined phase. And the maximum temperature of confined phase goes up and then becomes larger. And the minimum temperature of the confined phase comes down as n goes up. Okay, like this. And these two phases should be M-theory if we trust Itzhaki and the collaborators picture. And this phase is type 2A superstring. So there must be unknown phase transition, confinement to confinement transition, in order for the picture by Itzhaki and the collaborators to be consistent with the matrix model. And we want to say that that is actually the case. And by studying that picture, we can learn about the emergent geometry in terms of matrix model, and that should also apply to more generic radius shifting. And actually, I didn't realize until recently, but already in 1998, Banks, Fisher, Kleveroff, and Susskind wrote some paper, which is kind of speculative, but has really a great idea. And they wanted to study how black hole, evaporating black hole, which is also considered by Itzhaki and the collaborators, can be described by a matrix model. These three people are from BFSS, so it was a natural problem to think. And they thought that maybe, so we have n by n matrix in a matrix model. And they thought that those n degrees of freedom correspond, these n size, matrix size n kind of correspond to n particles. And among the n particles, m of them form a black hole, and some other particles describes graviton. And this black hole, this block shrinks, and many degrees of freedom change to graviton. And then that way, a black hole can be described. That's what they argued in 1998. And actually, I didn't know this paper, but we had also David Bernstein, who should be in that room, applied a similar idea to ADS-CFT. And we believe that this kind of picture can be true more generically. And more precisely, what is the meaning of this picture? I have to explain that. Okay. So in order to describe this kind of picture, we have to understand what meaning of this matrix, meaning of, or more specifically, scalar field in a matrix model or ML theory. So P plus one-dimensional super ML describes P-brane, and the P-brane is 1 plus P-dimensional object. And if matrix size is n P-brane are described in this theory. Okay, and this is actually starting point of these people's argument. And roughly speaking, eigenvalue of matrices correspond. So P plus one-dimensional theory has 9 minus P scalar field. And if you have P plus one-dimensional object in 1 plus 9-dimensional space, okay, string theory is defined in 1 plus 9 dimension. So if we have such object, there are 9 minus P transverse direction. And eigenvalue of these scalars corresponds to these coordinates. More specifically, imagine that the matrices are close to diagonal. Then this I runs from 1 to 9 minus P. Then you can collect one component of a 9 minus P matrices, and you can define vector in this space. And this is this transverse dimension. And so this vector made of one component would describe the location of the first DP brane in this space. And the two component describes the location of second D brane, and so on. And of course, there are off-diagonal entries. And if you imagine IJ component, they are somehow related to strings connecting ith and jth D brane. For example, in this picture, matrix size is 4 by 4. Imagine that the 1-2 component is small, or 1-2 component and the 2-1 component are small. That would mean not so many strings are excited between first and second D brane. And if a 3-4 component is large, that would mean a lot of strings are excited between third and fourth D brane. And actually, this kind of picture can be applied more generically, even at the strong coupling. This picture was given before ADS-CFT by Witten. And there was some argument that this kind of picture may not be useful for at the strong coupling where ADS-CFT can be applied. But actually, this kind of picture can work even at strong coupling. And for example, we can imagine such matrix configuration. This block has non-zero value plus quantum fluctuation. But this part is 0 plus some quantum fluctuation. Such a state can exist. And then we can interpret that this block describes black hole. And this is how idea by Banks, Fisher, Korevanov, and Saskin is realized in terms of metrics. So they had this kind, they didn't write this kind of thing explicitly, but I think they have this kind of picture. And the meaning was clarified, precise meaning was given last year in my paper. And also we can imagine how black hole is formed and evaporates. So we can imagine that this part is non-zero plus quantum fluctuation, but many other elements, matrix entries, are just 0 plus quantum fluctuation. Then each block would mean describe some object. And those objects come close, and the gravitational collapse takes place, and they form a big block. Then in this picture, diagonal entries are location of D branes, but off-diagonal entries are also non-zero. That would mean a lot of open strings are excited. That would mean bound state of a lot of D brane and strings are formed, and that's black hole. And then it can again emit those small blocks and evaporate. And this is how bank idea by Banks, Fisher, Kohlberg, and Saskip is realized in a precise sense. Maybe this picture doesn't look precise, but if you look at my paper, this is explained more precisely. And by using this picture, what the picture I showed about phase structure I showed for matrix model can be described more precisely in this way. So first we have deconfined sector, but this deconfined sector is actually completely deconfined phase. All D-brane nanostrings are excited. Then this confined sector is just 0 or 0 plus some small excitation, which corresponds to graviton gas. And in between, we have a small black hole phase. And if we look, so T critical, where there is a critical temperature below which confined sector is free energy global minimum, and above which the confined phase is global minimum. Okay, and then if temperature is between this T critical and this point, that would mean this phase has larger free energy. This phase has smaller free energy. And at this TC, below this TC, this phase has smaller free energy. This kind of phase diagram should exist. And actually we can check it numerically. And for example, we can see that below some temperature, order parameter for confinement, which is a Polakov loop, suddenly becomes 0. And I'm spending a lot of time, so I want to skip the detail. But for example, we can find this hitherto unknown confined phase. We can find this. For example, at the temperature 0.2, okay, in deconfined phase, if we use gravity result, energy has to be 0.08. However, at each fixed lattice size, we can take large n limit. And then we can see that, at each fixed n, we can take continuum limit. Number of lattice point goes to infinity. Then for 10 by 10 matrix, 12 by 12 matrix, or 6 by 16 by 16 matrix, we can always see that in continuum limit, energy is consistent with 0. And error bar, within error bar, it's close to 0.0 consistent with 0. And if we do a deconfined phase, energy has to be around here, around here, around here. But within error bar, it's inconsistent with this value. So we can actually see some phase where energy is clearly different from this value for the confined phase and clearly closer to 0. And also at each fixed lattice size, we can take a large n limit first. And then we can see that in those phases, this is green is Polakov loop. Polakov loop is going to 0. But in the confined phase, we can fit the value of Polakov loop at a higher temperature and extrapolate to t equals to 0.2. And if we do the confined phase, the value of Polakov loop has to be around 0.5. But we get 0. 0.5 is up here. So it's clearly different from the confined phase. And we can actually see such confined phase numerically.
Sorry,
so that's the
Masanori,
reason.
we have a question here from the audience.
Okay.
In your simulation, did you suffer from the issue of the large autocorrelation time?
We collected sufficiently many configurations. And for example, if you look at this history, and this is so thermalization take place. Polakov loop is coming down, and after that, the fluctuation. You can see fluctuation.
Yes.
And this seems to be like a kind of tunneling to the confined phase is taking place, but it didn't really quite. It didn't take place and coming back. And again, tunneling could happen, but came back.
Yes.
And this kind of event is observed multiple times. That would mean we have sufficiently many configurations. And in this case, I think this is larger n. This is n equals to 10. This is n equals to 16. With n equals to 16, tunneling is much more suppressed, and we can see nice fluctuation around here. And this is good enough for concluding that this is significantly different from 0.5. Because in the confined phase, Porakov loop has to be close to 0.5. Yeah. So it's true that the autocorrelation is very long. And in this case, we have to collect like 3,000 samples, but that's enough.
Okay. Yeah, usually if we have a side problem, autocorrelation time is an issue. Yeah.
It's separate from the sign problem, I think. But of course, with the sign problem, we need more precision, so we need even more samples. But okay. we have a sign problem a lot of. Yeah, some other technical issue.
Okay, indeed, I might just say experience that if some system suffer from the side problem issue, usually your sampling will be very autocorrelated. So it's why I wonder whether your error bar is not accurate.
But what I can say is modulo the assumption that phase point is fine. Okay. We have sufficiently many samples.
Yeah. Thank you.
Yeah. And I don't have a theoretical justification for phase quenching. Okay, so I spent almost an hour. Sorry, I went too quick, I thought. But the punchline is that using a very standard Monte Carlo method, we can see see that duality is actually working. In type 2A region, we can see not just supergravity, but also stringy correction agree. And I showed that the alpha prime correction was consistent, but also G string correction is also consistent with one band correction. And furthermore, not just a string theory. So in gravity side, we expect a phase transition between string theory and M theory. That can also be seen using Monte Carlo simulation. And I don't think anything other than numerical approach it could give us such dynamical property of a matrix model. So numerical method was certainly very powerful. However, lattice thermodynamics based on lattice, though it's very useful, it still has some limitation. And I want to encourage you to join activity to invent newer methods. Okay, so so we already had a good result, but we want to go to the moon, right? So we want to study new result. And I just explained some interesting problems to which Monte Carlo approach probably doesn't work. And that's related to property of each microstate and also real-time evolution. And I think machine learning or quantum simulation can be useful. Okay, so I already drew this picture before. So in this part, matrix value is non-zero plus quantum fluctuation, and this part is 0 plus fluctuation. And this excitation corresponds to black hole. Imagine that we trace out this part and then keep only black hole degrees of freedom. Then natural expectation is that we get entropy of a black hole, which is Bekenstein-Hawking entropy. And at large n and the strong coupling, we expect that this is precisely agree with the Bekenstein-Hawking in classical limit. But when the matrix size is finite, we would expect some quantum correction. That can have a very interesting information. But to do such computation, probably wave function is needed. Maybe we can do Monte Carlo, lattice Monte Carlo approach using a replica trick, but I'm not sure if that works. And I think if we have a wave function on a Hilbert space, then that is much more useful. But the Euclidean path integral does not give us a quantum state directly. Okay, so if we have a if we can directly get quantum state in Hilbert space, we can calculate the quantum correction to Bekenstein-Hawking more easily. But maybe with the Euclidean path integral approach, it's a bit harder. one even more interesting problem is somewhat a time-dependent feature. So this black hole emits graviton and completely evaporate. And qualitatively, we can determine time evolution of entanglement entropy between graviton and the black hole, and we can easily get so-called page curve. But so if we can determine the initial quantum state, initial state or final state or intermediate state, and calculate the entanglement entropy, then we can determine the page curve quantitatively, and we can see what kind of quantum gravitational effect is there. But again, wave function is needed. So lattice Monte Carlo approach may not be ideal for this. Furthermore, imagine that we have a black hole here and introduce some non-zero excitation here. That would mean we can use these blocks, which can be interpreted as some probe D-brane or probe particle. Okay, so we have black hole and we have some probe particle, and we can see how they interact. Well, even when this disappears, then it's just a BPS limit of black hole. So there's a BPS black hole sitting at the center of the bug, and we have some D-brane moving in that geometry. And then energy of such system should be described by Dirac-Born-Infeld action. And if we can actually check that, that would mean an ambiguous demonstration of how holographic space appear from a matrix degrees of freedom. So it's a perfect demonstration of emergent space. But again, to do such analysis, we should better have quantum state directly. And Euclidean perpendicular approach may not be optimal. And we can, I don't have time to explain the detail, but such problem can be reduced to a minimization problem with a certain constraint. And C.T. Hang and Sean Hartnell had a nice paper which do similar analysis of matrix model. And the approach is motivated by machine learning. More precisely, they parameterized, they did not consider full BFSS, but they consider a bit simpler matrix model. Okay, and the Hilbert space is huge, but they used a neural network to parameterize a wave function, and then tune the parameter using the standard operational Monte Carlo method. And it seems to be working pretty good. And we also, Enrico Rinaldi and C.T. Han and I and some collaborators also studied some other matrix model. And we also cross-check the result from other method, comparing with this approach and other approaches, and it seems to be working. So I think by pursuing this direction more, we can see emergent geometry or page curve or whatever interesting property. And that's something new, which is not lattice Monte Carlo. And time evolution can be even more exciting. So for example, we can in principle, if we have a quantum computer, we can see how these gravitons or probe D-branes move inside this black hole geometry, and how they interact with the black hole or how they scatter with each other. And that should, again, in gravity limit, should be described by Dirac-Born-Infeld, and whether it is true or not, or if we can see a correction to that, that is very fascinating thing. And we can actually see formation and the evaporation of black hole. If we can reproduce it in a quantum computer, that is very exciting. And of course, we would need a large scale error corrected quantum computer for such simulation. But we can check that in principle, it is straightforward. So assuming that error corrected quantum computer exists, what kind of formulation can work in principle, or how big resources needed? We can make such analysis. And it seems that the matrix model, though it looks rather complicated, which is very regularization is very straightforward, and simulation cost may not be too big compared to say, much simpler condensed matter system. So I think in future, we can use quantum computation for such physics and start thinking about such direction more seriously. And ideally, find a much simpler model, which we can study in a nearer future. That is very interesting direction. And so this is my final slide. So thermodynamics via Monte Carlo simulation has been very successful. And we could see type 2A superstring theory precisely is precisely due to matrix model. But now we go even beyond that point. And we can see M theory is actually described by matrix model. And I want to study more in this aspect in the next 3-4 years. At the same time, though this is very exciting, new techniques are needed as well, and probably can do even more interesting physics. And I think in this direction, there are many low-hanging fruits for newcomers. So if I were in Korea now, I wanted to spend the time for new friend and wanted to discuss this direction. But hopefully, even though it's remote, I can have time to chat with the participants. Thank you very much.
Okay, thank you very much, Masanori, for this talk. It's time for questions.
So, is somebody speaking now? Sorry.
Yeah, Jungi speaking.
Hi. Yeah,
Hi.
Microphone. I just yeah. So thank you for a nice talk. And here you mentioned that it's black hole evaporation.
Mhm.
And Monte Carlo simulation is just kind of finding the minimum. So
Yes.
it would be some kind of stationary state. If I'm not, it's naive. I'm not good at this quantum Monte Carlo simulation, but it probably see that this kind of a minimum or ground state or equilibrium state. But the black hole evaporation is kind of it's I don't know how to say, but it looks like in the end it's time evolved to the complete evaporation. So is it? Can you apply this kind of quantum Monte Carlo simulation to this black hole evaporation problem, which is time dependent?
You mean thermodynamics simulation?
Thermodynamics okay, but like some you have black hole and very long time later, like after page time, black hole will be evaporation. Seems that it's a non-equivalent type, but
yes. So that's a reason that we need a quantum computer. So in principle, like imagine that. So first, we can do thermodynamics, and from that we can study the property of metastable state. So I think we can have a good guess about the initial condition from lattice Monte Carlo. And then by using that as input, we prepare a good initial state on quantum computer. And then that initial state evolve with time. And then it should gradually emit small blocks and evaporate. But because you're right, it's a non-equilibrium problem. And that's the reason if we do lattice Monte Carlo, it's hard to study such property. However, if, for example, the final state would look like this. Initial state would look like in this picture, black hole evaporation. This is initial state. This is final state. But for example, if we focus on Porekov loop, for example, Porekov loop evaluated by such state and such state. They are different, and we can have a good guess about that. So maybe by constraining observable like Porekov loop, we can study, for example, this kind of phase by using lattice Monte Carlo, or we can study this kind of phase by using lattice Monte Carlo. And I think we can study them separately. But the time evolution is very hard.
So when you say time evolution, do you use is it the Hamiltonian of the BFSS?
Hamiltonian time evolution, yes. So in that sense, it's not the Euclidean theory. It's a Minkowski signature.
Oh, I see. Okay.
Yeah.
Okay.
Other questions? Maybe from chat, from online participants? It seems not. So yeah.
Actually, yeah, I have one more question about the page. So how I saw some paper on this probably including you, but this kind of calculate the entanglement entropy of the matrix model by some target space. So using that, can you also reproduce the page curve, or still it's a kind of goal?
We can actually get page curve, yes. And that can be a bit longer story. So I encourage you to invite me for another regular seminar at APCTP. Next time in person.
Okay.
So in late summer, I have to go to Japan. So then Korea is very close. So I can drop by hopefully.
Yeah.
Or online seminar is also fine.
No more questions? Okay, if not, we can thanks Masanori again. And this concludes our today's session. Do you have some announcement? Good. Thank you very much.
So is there like some discussion session I can join later? Today, actually, I have to go somewhere soon.
Yeah, we also, for the last session, we have to go to the dinner. So we should organize another discussion session.
Yeah, yes, that's great. So not just today, but tomorrow, and I will try at least morning session, evening session for you, morning session for me. I try to join. Okay, bye then.